Okay, thank you. Hello, everyone. So before I start, let me indeed thank the organizers for their efforts in organizing this nice workshop. So I will be discussing dissipative impurity dynamics in one-dimensional quantum liquids. And this is the work done together. Some parts are done together with Mathilde Hugbart, who is a postdoc at LPT, and some parts with Zoran Ristivojevic, who is a CNRS researcher. So I will start by reminding you about impurity problem. So if you think about a single distinguishable particle that we will be referring to as an impurity coupled to the environment, this is a fundamental question and relevant for a large class of problems. Here I give you some early famous examples like length shift, where you can think of an electron in a hydrogen atom as an impurity, and in this case the environment is actually the quantum electrodynamic vacuum. Then indeed a lot of efforts were focused on the motion of helium-3 atoms in the superfluid helium-4. And let me also mention one condensed matter example where one studies the motion of an electron in a crystal. Of course, the ions tend to screen the electron charge, and electron gets dressed by a cloud of photons. And to this quasi-particle we refer as a polaron. Okay, so polaron today is used in wider sense for any mobile particle coupled to an environment and dressed by a cloud of excitations of that environment. Okay, I should say that indeed the progresses in the field of cold atomic gases opened a new door into physics of impurity due to, as you know, possibility to control dimension, that there are no defects, we have a good isolation from the external sources of decoherence, and we can tune the interaction strengths. All right, so I will be discussing an environment that is made of interacting one-dimensional bosons, and we heard a lot about the Lieb-Rinninger model, where the first part is the kinetic energy and is the mass of the bosons, and we do have a contact like a repulsion between the bosons. So here, in addition, we have a single impurity, so this is the kinetic part, and it couples locally to the bosons in the system. So what happens if you think about, for example, repulsive impurity? It depletes the condensate density, so this is the density as a function of x. And here is the position of the impurity, and the width of this depletion is proportional to the coherence length, but also depends on the velocity of the impurity and its mass. And this dip moves together with the impurity. All right, in addition, impurity actually imposes a phase drop across it, and that's why we do have a phase gradient in the remaining part of the system if you think about periodic boundary conditions. Okay, so in the first part of my talk, I will be discussing impurity that is injected in the system of the bosons with a given momentum P0, then we will follow its relaxation. Or if you want to think in terms of the quench, interaction with the system is just quenched on the initial moment. Let's start discussing the weakly interacting bosons, and to get some understanding of the phase scales in the problem, we will start by solving this time-dependent Gross-Vitebsky equation, where we do have interaction between the bosons, interaction with the impurity, and in addition we have this drifter, where V of t is actually the impurity velocity at the moment t. What happens is that initial momentum, actually some part is channeled into Bose gas. In the case of infinitely heavy impurity, this problem, in the stationary case, this problem was considered by Hakim, where he finds analytic solution for the stationary state. In the case of finite mass impurity, this can be easily modified, and we can find the stationary state, and we can evaluate the energy of the system in the stationary state as a function of the total momentum of the system. So this is the curve that I plot here. And we do see that energy actually is periodic function of momentum with a periodicity that is set by the boson mean density n naught. I should say that this is indeed the peculiarity of one-dimensional systems. And indeed, if you think about drawing a system with a small force, then you will have a Bloch oscillations that were studied theoretically, and also we have nice experiments in Innsbruck group, but I will not talk about that. And in addition, you can evaluate the impurity velocity, which is just a derivative of this curve with respect to the total system momentum. So this is what one expects to get from analytic solution. And of course, impurity velocity in the stationary state is smaller than the critical velocity, right? So this is the maxima set by the critical velocity. All right, so let us look how the dynamics is performed if we start from this far from equilibrium state. So this is a physical picture that emerges. What happens is that impurity perturbs the density locally, causing the emission of dispersive density waves that move away, and they carry some energy, and we indeed get to the stationary state locally around impurity. Of course, in this process, the impurity velocity goes down, so there is some friction in the system, and then the long scales, we reach stationary state. And in that case, since we are at zero temperature, the impurity does not come to a full stop, since this is a hallmark of superfluidity. All right, so let us take a look at the dynamics in different corners of the phase space. So if we, for example, here I keep the mass of the impurity constant and its coupling constant is a constant, and I just change the initial velocity, then we do see that the relaxation becomes somewhat slower, and moreover we do see this non-monotonic behavior of the impurity velocity. However, more interestingly, impurity dynamics strongly depends on the impurity mass. Here we have the same initial velocity, the coupling constant is the same, but we have different curves for different impurity masses.
Sorry, what
yes?
is small v again? Is it the sound velocity?
Small v, yeah, is the sound velocity. So impurity velocity is measured in the units of the sound velocity. Yeah. So what do we see? We see actually that heavy impurity can change the sign of the, change direction of the motion. Initial velocity is positive, final one can be negative. We do see that the relaxation times get bigger, relaxation is slower. And if you think about this characteristic time where the minimum in the velocity appears, it seems that it scales actually with them if the mass of the impurity is bigger than the mass of the bosons. So the relaxation really becomes slower. And even more, we do observe some oscillations here that I'm going to discuss now in more detail. Okay, so we saw what happens if we increase the initial momentum, if we change the mass, and what happens actually if we change the coupling constant of the impurity to the bar. So this is actually the picture. Relaxation becomes longer and longer if the impurity coupling constant gets smaller, and it seems that relaxation times actually is inversely proportional to the impurity coupling constant. In addition, we do see that the oscillations that I was referring to, so there is a first part of the dynamics, which is actually the rapid drop of the velocity, right? And then there is this region where we do have damped oscillations before coming to the stationary state. We do see that if impurity is weakly coupled, smaller G tilde is, the oscillations are more and more pronounced. And I started the talk by saying you that we do know what are the stationary states, and actually for each velocity we have two stationary states, but here we do find that impurity does not oscillate between these two states during those oscillations, but rather remains in the vicinity of one stationary state. Also, let me mention that this type of behavior was predicted first for the integrable models, and it was dubbed quantum flutter. So I would not say the phenomenon is the same, it resembles, so these authors actually pointed out that the phenomenon that they are interested in cannot be described this hydrodynamic picture that actually we indeed use. Furthermore, if the impurity coupling increases, the final velocity rate goes down, decreases. Okay, so so this was the dependence on the impurity coupling constant, but if you increase the mass of the impurity above the so-called critical mass, actually what happens is that the ground state develops this cusp-like behavior, right? And the second state that I was mentioning is no more the ground state, actually, of the system. How this cusp-like behavior manifests in the dynamics, so this is what I'm going to tell you. So this is actually the final velocity as a function of the initial one, and that one would expect from this analytic solution. And those points are actually results of the numerical simulation. So what do we see? We see actually when we reach the critical velocity, system relapses, but it relapses in that way that gets rid of the energy by emitting the solitons. And this is the reason why we have this disagreement with the analytic theory, because it does not take into account emitted density waves and neither the solitons. If we move further in the velocity, the depth of the solitons becomes bigger and bigger, meaning they are more and more energetic, and we do observe dark solitons for some bigger initial velocity. All right, how does it manifest in this emission of the solitons in the impurity dynamics? So here I show the velocity as a function of time, and this is this point where the soliton emission we do see for the first time, so dynamics becomes smaller. So as you see, I plotted it separately because indeed the time scales are longer, and the impurity in this case also changes the direction of its motion. All right, so this was the story about zero temperature dynamics in the case of equally interacting bosons. And now I switch to the other topic. Actually, I will be now interested in the friction force that system exerts on the impurity, on the flow impurity, meaning that we are now in the stationary state, velocity is smaller than a critical one, and we want to calculate what is the friction force once the temperature is non-zero. Okay. Okay, so indeed there are nice theoretical works, the old one by Castronetto and Fischer, that show that the friction force scales as a fourth power of the temperature. And later on, Gangart and Kamenev, they have calculated the prefactor of this law. They have expressed it in terms of phenomenological parameters of the system, like impurity dispersion relation, effective mass, chemical potential of the boson, that in a general case are unknown parameters. Okay, so I should point out that Castronetto and Matthew Fischer, they use the Lagrange-Liquid description, and Gangart and Kamenev, they use so-called nonlinear Lagrange-Liquid, taking into account some curvature. However, both theories are indeed limited to the low energy description of our system, and that's why to the variable temperatures. So what we have done, we have started from the microscopic description of the system, and we have evaluated the friction force. I will start by showing you the results for weakly interacting bosons first. In that case, one can take into account fluctuations, solving the Bogoliubov-Dengen equations, and evaluate the friction force in a wide range of the impurity coupling constants and temperatures. So, okay, so I should explain. So this is first I will discuss also heavy impurity, where the friction force can be expressed in this way. So we have the mass of the bosons, chemical potential of the bosons, mass of the impurity, and P is the momentum of the impurity. And then we have a dimensionless function that depends actually on two dimensionless parameters. One is the dimensionless temperature, and the another one is dimensionless impurity coupling constant measured in the units of the sound velocity. So this is the schematic phase diagram. I should say we have analytic expression that describes all these crossovers, but I just show you the scaling of the force in different regions of this phase diagram. So what do we see? First, we do see this T to the 4 scaling at low temperatures as is expected. But we do find the region where this T to the 4 scaling applies. Okay, we have the boundaries. And even more interesting is that if we increase the impurity coupling constant, this T to the 4 scaling region shrinks down, and we have a new regime where the friction force behaves as the second power of the temperature. So what happens actually is that Bogoliubov quasi-particles are completely reflected off the impurity, and this is why we have a new scaling. Okay. Even more, I should say, although the calculations were performed for weakly interacting bosons, we do expect this new regime to appear at arbitrary gamma. However, in that case, we do not know what is the boundary where this regime should be realized. At higher temperatures, we do have a linear dependence, mostly apart from some logarithmic corrections. All right, so what is the physical picture behind this rich phase diagram? Actually, yes.
Is it the force below the critical speed for supersonic motion we calculate here?
Yeah, this is the force exerted by the bosons on the impurity, which is slow, meaning more than a critical velocity shift. Yeah, so the physical picture behind these different crossovers is very simple. So this is the reflection amplitude of the Bogoliubov quasi-particles at the momentum k for strong coupled impurity. And we do see here that we have different regimes. We have small k square behavior below this scale, and then Bogoliubov quasi-particles are completely reflected of the impurity, and in strong k, the amplitude decays in this way. So if you think that actually the temperature determines what k values are thermally excited, here k you can replace by t, and you see when you're going from this region to this one, you lose 2 powers of the k that manifests itself in losing 2 powers actually of the temperature, roughly speaking. And this additional crossover is manifested here. Okay, so maybe I just mentioned if you would think about scattering of the free particles on the delta potential, your reflection amplitude would be 1. They would be completely reflected if k goes to 0, and here we have somewhat different things. All right, so maybe just let me mention that, okay, for example, if you go from the yellow to this green region, so this is the photoanalytic expression that is nonlinear function of impurity coupling constant G tilde, which describes actually this crossover here. All right. So, if you think about heavy impurity, having initially momentum p naught, it scatters of the thermally excited quasi-particles, and the process is stochastic. So you can write down, you can consider the time-dependent distribution function for the impurity. You can write down the kinetic equation, and in the case of the heavy impurity, kinetic equation can be simplified and simplifies into Fokker-Planck equation that in this case can be solved exactly, and this is actually a famous Orstein-Uhlenbeck process, but this time in the momentum space. So P naught is the initial momentum, and what is important here is this relaxation time tau that is actually determined by this friction force that I have discussed previously. If you look at the variance, it behaves in this way, so T is the temperature, and at short times, I mean, if you expand this, you get indeed the diffusive motion in the momentum space with the diffusion coefficient that is also determined by the friction force. So here I have sketched how the delta-like distribution evolves in time. All right, so as I said, I showed you some results for the heavy impurity. One can perform also the calculation for arbitrary mass impurity. And for example, in the V-coupling case, this is how the friction force looks like. Well, I don't want you to look at all this nonlinear dependence, but if you look at this coefficient in front, then indeed you see that in the so-called Young-Goda model, which is integral model, which is realized when the impurity coupling strength equals the repulsion between the bosons, and the mass of the impurity equals the mass of the bosons. Indeed, in this case, there is no friction. Impurity propagates without friction. Furthermore, you do see that this coefficient vanishes under less restrictive condition, meaning this one, which is not integrable case, and in that case one has to consider higher order processes in the scattering matrix element, and we do see dramatic change of the friction force, which now behaves as the 8th power of the temperature. And I must say, although this is the low temperature result, the nonlinear quasi-particle dispersion becomes important, and that's why using the Laffinger liquid like theories, it cannot be described. All right, so finally let us come to the strongly interacting bosons. As Jerome explained us, in the case when gamma is infinitely big, if we discuss it on the Girardot limit, the bosons can be mapped to the non-interacting fermions, where in some sense Pauli principle mimics this strong repulsion. But actually this mapping works also for gamma which is big, but not infinitely big. And in this case, there is additional term which is actually attraction, weak attraction between the fermions. So this is known as challenge the higher model. In this case, one can also study the friction force exerted on the impurity. And for example, in this case, if you consider impurity with a momentum P, the leading order term at low temperatures comes from the scattering of the impurity of two fermions with momenta P1 and P2. And this is the outgoing configuration where Q is the final momentum of the impurity, and these are the momenta of the fermions. Okay, so in this case, one has to discuss different processes. We are at low temperatures, that's why the fermions are situated around the Fermi points. Impurity is slow, and if the fermions are sitting around different Fermi points, this is why I call this 1-1 process. I should say this is the initial configuration. Due to the momentum conservation, the final configuration will be also of this type. And then we do have other kind of processes where the fermions are situated around the same Fermi point that I call 0, 2, or 2, 0 processes. One can analytically evaluate the friction force, and I will not be showing you the full analytic expression, but just the scaling. And indeed, these 1-1 processes are the most relevant ones at low temperatures, giving this T to the 4 scaling, and these processes give higher order terms that scale as the 10th power of the temperature. All right, so if there is a possibility to tune the interactions in cold atomic gases using the Feshbach resonances, one can indeed tune the repulsion between the bosons to some special value such that this coefficient in front of the T to the 4 row vanishes, and one can design desired friction in the system, which in this case will indeed behave as the 6th power of the temperature. All right, so with that I come to the conclusions. I discussed the impurity dynamics in one dimension on quantum liquids, and we saw that it can be quite rich. So what next? I shortly mentioned that Bloch oscillations attracted a lot of attention on theoretical and both on the experimental side. However, I do find that there are many unanswered questions. Furthermore, one can think about creating some quantum probes composed of the impurities, such that we can extract some information about the system in a non-destructive way, like having the thermometer, for example, in this case that I have discussed. Also, a very interesting question is the bipolar formation, where actually, if you have, for example, two impurities, there will be mediated interaction between them. In some cases, it is indeed attractive one and can lead to the quantum mechanical bound state of two polars. And let me mention that all those results indeed call for more detailed studies of the same question in higher dimensions. With that, I thank you for your attention.